Welcome back to the Nocturnal Astronomer. I am Atlas Reed, and tonight I want to start with something that sounds impossible, but has been measured, tested, and confirmed again and again. Right now, somewhere above your head, satellites are experiencing time itself moving at a different pace than it does for you. Not because their clocks are broken, because time itself, according to everything we have observed, is not one single river flowing at one single speed for everyone. It bends, it stretches, it slows near heavy things and near great speeds, and it does this quietly, without asking permission, all the time, everywhere. Tonight, we will talk about time dilation and the relativity of now. We will talk about tiny particles that should not survive their fall to Earth, but do. About clocks flown on aeroplanes, about the satellites that guide you home, and about what it might mean that there may be no single universal moment that everyone, everywhere, shares. Let's dive in. Part 1. What we mean when we say right now. For most of human history, nobody questioned what right now meant. A clock in one town and a clock in another town, if both were wound correctly, agreed with each other. Time seemed to march forward everywhere at once, the same beat, the same rhythm, shared by every person on Earth without a single exception. This feeling is so natural that we rarely examine it. When you say something is happening right now, you assume that a person on the far side of the planet, and a person on the moon, and a person on a spacecraft far beyond our solar system would all agree with you. It feels obvious. It felt obvious to nearly every thinker before the 20th century. Isaac Newton described time as something absolute, flowing equably, without relation to anything external. In his view, there was one clock for the whole universe, ticking the same way regardless of where you stood or how fast you moved. For over 200 years, this idea worked well enough for nearly every purpose we had. Then, in 1905, a young patent clerk in Switzerland named Albert Einstein published a paper that quietly rewrote this assumption. He was not trying to be provocative. He was trying to solve a puzzle about light, motion, and electricity that had been bothering physicists for years, one that Newton's picture of time could not fully explain. Einstein's answer required abandoning the idea of one shared now for the whole universe. Instead, he proposed that time passes differently depending on how fast you are moving relative to someone else. Two observers moving at different speeds would disagree about how much time had passed between two events. Neither would be wrong. This is called the relativity of simultaneity. Two events that happen at the same moment for one observer may happen at noticeably different moments for another observer, if that observer is moving relative to the first. This is not a trick of measurement. It is, as far as we can tell, a real feature of how time and space are woven together. Picture two travelers moving past each other at a steady speed, each one carrying a precise clock. If they could somehow compare those clocks in that passing moment, each traveler would find that the other clock seemed to be running slow. Neither traveler is wrong. Time simply looks different from where each one stands. This sounds like a contradiction, but it only feels that way because we are used to thinking of time as a fixed, shared backdrop, the same for everyone, like a stage upon which everything else happens. Einstein's insight was that time is not the backdrop. Time is part of the performance itself, shaped by motion and by gravity. Physicists now describe space and time together as a single fabric, often called space-time. Movement through space and movement through time are linked. The faster you move through space, the slower, from an outside point of view, you move through time. It is as if there is a fixed total speed shared between the two, and increasing one lowers the other. None of this shows up in daily life because the speeds we experience, cars, planes, even rockets, are so small compared to the speed of light that the effect is nearly impossible to notice. But nearly impossible is not the same as zero. And as we will see, when we build instruments precise enough, the effect becomes undeniable. Part 2. The speed of light and why it matters. To understand why time bends, we first need to talk about light, and about one very strange fact that 19th century physicists kept running into. No matter how fast you move toward or away from a beam of light, you always measure it traveling at the same speed. This should not make sense, and yet it does. Ordinarily, speeds add together the way we expect. If you throw a ball forward from a moving car, the ball moves faster relative to the ground than it would if you were standing still. Throw it backward and it moves slower. Light refuses to behave this way. Its speed, measured by anyone in any direction, always comes out the same. This was confirmed by careful experiments in the 1880s, most famously by Albert Michelson and Edward Morley, who tried to detect the Earth's motion through a supposed medium filling all of space. They found nothing. Light moved at the same speed no matter which direction they measured it, no matter how the Earth itself was moving. For years, physicists tried to explain this away, inventing complicated ideas to preserve the old picture of time and space. Einstein took a different approach. He simply accepted that the speed of light truly is the same for every observer, and then asked What else would have to be true for that strange fact to make sense? The answer he found was radical. If the speed of light stays fixed, no matter how you move, then something else has to give. That something else turned out to be our assumptions about time and distance. Moving clocks tick more slowly, and moving rulers shrink slightly, all so that the speed of light can remain constant for everyone. This idea that the speed of light is a true cosmic limit, one that nothing carrying information or mass can reach or exceed, became one of the cornerstones of modern physics. Roughly 186,000 miles pass in a single second, a staggering figure, and yet it is not infinite. It is a firm boundary built into the universe itself. Because light has a speed rather than arriving instantly, it also carries a strange gift. When you look at a star tonight, you are not seeing it as it is right now. You are seeing light that left it years, or centuries, or even far longer ago. In a real sense, the night sky is a window into the past. Some of the light reaching your eyes tonight left its source before recorded human history began. A star you glance at for a moment might have already changed or even faded, and you would have no way of knowing yet. The delay is not a flaw in our instruments. It is simply how light travels through the vastness between stars. This delay grows the farther you look. Nearby stars show us a past only a handful of years old. Distant clusters of stars show us a past reaching back millions or billions of years. Looking outward into the universe is quite literally looking backward through time, layer after layer. The deeper you look, the older the light. The fixed speed of light is the seed from which all of time dilation grows. Because that speed cannot change, everything else, including the flow of time itself, has to bend around it. It is a strange kind of order hidden underneath the universe, one constant number that quietly reshapes how time behaves for everyone and everything. Part 3. How motion bends the flow of time. Special relativity, the theory Einstein introduced in 1905, gives us a precise rule for how much time slows down as speed increases. At everyday speeds, walking, driving, even flying in a plane, the slowing is so tiny it would take incredibly sensitive instruments to notice it at all. But as speed climbs closer to the speed of light, the effect grows dramatically. At half the speed of light, a moving clock ticks noticeably slower compared to a clock that stayed still. At 99% of the speed of light, a clock would tick many times slower. The closer you get to light speed, the more dramatic the slowing becomes. This is often called time dilation, a lengthening of time for a moving observer as seen from someone who is not moving with them. From the moving traveller's own point of view, nothing feels unusual at all. Their heartbeat, their thoughts, their aging all proceed normally. It is only when compared to someone else that the difference appears. This leads to a strange and famous idea called the twin paradox. Imagine one twin stays on Earth while the other boards a spacecraft traveling near the speed of light, journeys far into space, and then returns. When the traveling twin steps back onto Earth, less time will have passed for them than for the twin who stayed behind. The traveling twin might return having aged only a few years, while decades have passed for their twin on Earth. Both experienced time normally from their own perspective. Neither felt time speed up or slow down while it was happening. Yet when they meet again, their clocks and their bodies tell two very different stories about how much time passed. This is not merely a thought experiment confined to chalkboards. It reflects something we have now measured directly, using atomic clocks so precise they can detect differences of mere billionths of a second. The predictions of special relativity have been tested repeatedly, and every time the universe has agreed with Einstein rather than with our everyday intuitions. Time and space are connected, part of the same underlying structure. Every observer moves through that structure at a steady overall pace. Some of that pace goes toward movement through space. The rest goes toward movement through time. Someone moving very quickly through space experiences time passing more slowly than someone standing still. This borrowing is not free, and it is not something you could exploit to somehow gain extra years of life relative to everyone around you while staying home. It only appears when two clocks that started together are brought back together again after moving differently through space. Comparing clocks, not simply owning one, is what reveals the effect. None of this required new mathematics beyond what students already learn, only a willingness to take the constant speed of light seriously and follow the logic wherever it led. Einstein's genius was not inventing complicated equations. It was trusting a strange, simple fact fully, even when it demanded giving up comforting and familiar ideas about time. What makes this section of our story remarkable is how quietly it sat, mathematically complete, for decades before technology caught up enough to test it directly. The universe had already been behaving this way the entire time. We simply needed instruments sensitive enough and clever enough experiments to finally catch it happening in front of us. Part 4. Falling Particles That Prove Time Bends. One of the earliest and most beautiful confirmations of time dilation involves something you cannot see, cannot hold, and yet is raining down through the atmosphere above you, at this very moment. These are particles called muons, cousins of the electron, created high above us when cosmic rays strike molecules in the upper air. Muons are unstable. Left alone, a muon decays into other particles after an incredibly short average lifetime, only about 2/millionths of a second. Given how quickly they vanish, and given how far above the ground they are created, simple arithmetic suggests that almost none of them should survive long enough to reach the surface of the Earth. And yet, when physicists count muons arriving at ground level, they find far more of them than that simple arithmetic predicts. Detectors placed at mountain tops and at sea level, comparing how many muons appear at each height, discover something that should be impossible if time passed the same way for the muons as it does for us. The explanation is time dilation. Muons created high in the atmosphere are moving at speeds extremely close to the speed of light. From our point of view, standing still on the ground, their internal clocks, the process that leads to their decay, run far slower than expected. Their brief lifetime is stretched out, giving them enough extra time to reach us. This experiment was carried out carefully in the 1940s by physicists Bruno Rossi and David Hall, who measured muon numbers at 2 different altitudes and compared the results to what ordinary, non-relativistic physics would predict. The numbers only matched once time dilation was included, offering some of the earliest solid evidence supporting Einstein's ideas. From the muon's own perspective, nothing strange is happening at all. It still only survives for its usual brief lifetime. What has changed from our outside vantage point is how much time that brief lifetime corresponds to, stretched by its tremendous speed. Time dilation works both ways here, in a way that also connects to shrinking distance. From the muon's point of view, another effect appears instead. Because it is moving so quickly, the very distance through the atmosphere that it must fall appears shortened to it. This related effect is called length contraction, and it shows that time dilation and shrinking distance are 2 sides of the very same relativistic coin. Whether you explain it through time stretching for us or distance shrinking for the muon, the 2 explanations agree perfectly on the final result. More muons reach the ground than old-fashioned physics would allow. This kind of agreement from 2 very different points of view is exactly the kind of confirmation that convinces careful scientists. What makes this proof so moving to me is its scale. These are not spacecraft, not enormous instruments built at great cost. These are tiny, invisible particles formed by cosmic rays crashing into our atmosphere, offering us proof of one of the strangest ideas in all of physics, falling gently and constantly through the sky above every one of us. Every single day, without any announcement, without any fanfare, the atmosphere above your head performs a quiet demonstration of relativity over and over again, particle after particle, each one a tiny messenger carrying evidence that time truly does behave differently depending on how quickly something moves through the world. Part 5. Clocks flown around the world. By the middle of the 20th century, physicists had strong theoretical reason and indirect evidence to trust time dilation. But two researchers wanted something even more direct, something that ordinary people could understand without needing to know anything about muons or cosmic rays. They wanted to fly actual clocks and simply watch what happened. In 1971, physicist Joseph Hafele and astronomer Richard Keating carried out an experiment that has since become famous. They loaded 4 extremely precise atomic clocks onto commercial airplanes and flew them around the world, once heading eastward and once heading westward, while an identical set of clocks remained at rest at a laboratory. Atomic clocks measure time using the extraordinarily steady vibrations of atoms, allowing them to keep time far more precisely than any mechanical or quartz clock. Even so small an effect as relativistic time dilation, ordinarily far too tiny to notice, could be picked up by instruments this sensitive, especially once compared against a clock that never left the ground. When the travelling clocks returned and were compared to the ones that had stayed behind, a tiny but real difference appeared, just as relativity had predicted. The clock that flew eastward, moving with the Earth's own rotation, ended up slightly behind the stationary clock. The one that flew westward, moving against the Earth's rotation, ended up slightly ahead. The differences were small, measured in mere billionths of a second, but they matched the predictions of both special and general relativity remarkably well. Special relativity accounted for the effect of speed, while general relativity accounted for the effect of altitude, since the planes were flying at a height where Earth's gravity is very slightly weaker. This experiment mattered enormously because it moved relativity out of the realm of subatomic particles and thought experiments and placed it firmly inside something almost anyone could picture. Ordinary aeroplanes, ordinary clocks, a familiar trip around the globe. It showed that time dilation is not some obscure effect confined to extreme speeds or exotic laboratories. It happens gently, quietly, every time something moves relative to something else, or sits at a different height in a gravitational field. The Hafele-Keating experiment simply made that gentle, quiet effect visible, using tools precise enough to catch it, tools that any well-funded physics laboratory of the time could, in principle, reproduce. Since then, the experiment has been repeated and refined many times with even more precise clocks, and the results have held up consistently. Physicists have also compared clocks kept in laboratories at different altitudes, even a difference of a few feet, and detected tiny differences matching what relativity predicts, confirming the effect at smaller and smaller scales. What I find soothing about this story is how ordinary its setting was. 2 scientists, some commercial flights, careful clocks, and a question worth asking. From that simple arrangement came confirmation of one of the deepest truths we know about the universe. A reminder that profound discoveries do not always require exotic settings, only patient curiosity. Part 6. Time and the satellites above our heads. If time dilation felt like an abstract curiosity confined to physics laboratories, that changed the moment it became something engineers had to account for in a system many of us rely on every single day. I am talking about satellite navigation, the technology that quietly guides ships, planes, and the phone in your pocket. These satellites orbit high above the Earth, broadcasting extremely precise time signals down to receivers on the ground. Your device compares signals from several satellites at once, and by measuring tiny differences in when each signal arrives, calculates exactly where you are. The whole system depends entirely on those onboard clocks being accurate to an extraordinary degree. But those satellites are affected by 2 competing relativistic effects at once. Because they move quickly through their orbits, special relativity says their clocks should run slightly slower compared to clocks on the ground. Because they orbit far above the Earth, where gravity is weaker, general relativity says their clocks should run slightly faster compared to clocks on the ground. These 2 effects do not cancel out evenly. The weaker pull of gravity at that altitude wins out over the effect of their speed, meaning the satellite clocks would drift ahead of ground-based clocks if left uncorrected. The difference amounts to about 38 millionths of a second gained by each satellite clock every single day. That may sound too small to matter, but because these systems rely on timing accurate to billionths of a second to calculate your position, even this tiny daily drift would cause serious errors. Left uncorrected for even a single day, positioning errors could grow to several miles, turning a system meant for precision into one that is simply unreliable. Engineers solved this by deliberately adjusting the satellite clocks before launch, slowing their ticking rate very slightly so that once in orbit, combined with the relativistic effects, they would match ground clocks as closely as possible. In other words, relativity had to be built directly into the engineering, not treated as an afterthought or a footnote. This means that Every time your phone finds your location, whether you are walking somewhere new or simply checking a map, you are relying, whether you realize it or not, on Einstein's understanding of time and gravity. The theory is not confined to textbooks. It is quietly embedded in one of the most widely used technologies of our era. It is a strange and lovely thought that the same insight which explains muons falling through the atmosphere and clocks flown around the globe on airplanes also keeps your navigation running smoothly today. Relativity is not distant or theoretical. It is functioning right now in satellites passing silently overhead as you go about your evening. I find something reassuring in this, an idea that once seemed almost too strange to be true, one that challenged our most basic assumptions about time, has become so well confirmed that engineers now depend on it daily, without controversy, simply as a known and trusted fact, woven quietly into the technology guiding so much of modern life. Part 7. How gravity also slows the clock. So far, we have mostly discussed time dilation caused by motion. But Einstein's later theory, general relativity, published in 1915, revealed another way that time bends, one caused not by speed, but by gravity itself. According to this theory, time runs more slowly the closer you are to a massive body. This might sound similar to the effect of motion, but it comes from an entirely different idea. General relativity describes gravity not as a simple pulling force, but as a curving of space-time itself, caused by mass and energy. Planets, stars, and other massive bodies bend the fabric around them, and clocks respond to that curve. Space-time curves around massive objects, the same way any surface curves under weight. The curve becomes steeper the closer you get to the object. Clocks position closer to the object within that steeper curve tick more slowly than clocks positioned farther away where the curve is more gentle. This means a clock on the ground floor of a tall building, slightly closer to the center of the Earth, ticks ever so slightly slower than a clock on the top floor. The difference is minuscule, but it has actually been measured directly, using clocks precise enough to detect the tiny variation caused by even a small change in height. One of the earliest tests of this idea was carried out in 1959 by physicists Robert Pound and Glenn Rebka, who measured how light traveling upward through a tower on Earth lost a tiny bit of energy as it climbed away from the planet's gravity, a subtle shift matching exactly what general relativity predicted for gravitational time dilation. Since then, gravitational time dilation has been confirmed in many settings, including comparisons between clocks on the ground and clocks aboard aircraft or satellites, and even comparisons between clocks placed on shelves only a small distance apart in height within the same laboratory, using the most sensitive atomic clocks scientists have ever built. The effect grows stronger the closer you get to an extremely massive or dense body. Near a neutron star, for example, time would tick noticeably slower compared to somewhere far from its gravity. The stronger the gravitational pull, the more dramatically time slows for anyone or anything sitting close enough to feel that pull strongly. This gravitational slowing also explains part of why the satellite clocks we discussed earlier run faster than clocks on the ground, since they sit farther from Earth's center, where gravity's grip is gentler. Motion slows their clocks somewhat, but the weaker gravity at their altitude speeds those same clocks up even more, tipping the overall balance. Gravity and motion, then, are two separate roads leading to the very same destination, a flow of time that is not fixed, not universal, but shaped by where you are and how you are moving. Time, it turns out, listens closely to its surroundings, adjusting itself quietly according to rules written into the shape of space-time itself. Part 8. Near the edge of a black hole. If gravity slows time gently near ordinary planets and stars, imagine what happens near the most extreme gravitational environments the universe has to offer. Black holes represent gravity taken to its furthest known extreme, regions where mass is packed so densely that not even light can escape their pull once it strays too close. Around every black hole lies a boundary called the event horizon, the point past which nothing, not light, not matter, not information of any kind, can return. As you imagine approaching this boundary, the gravitational time dilation we discussed earlier grows more and more dramatic, stretching further and further from the ordinary pace of time we know. To a distant observer watching something fall toward a black hole, the falling object would appear to move more and more slowly as it neared the event horizon, its clock ticking slower and slower, its light stretching and dimming, until it seems to freeze in place, never quite crossing that final boundary, at least from the outside view. From the perspective of whatever is actually falling, though, time would feel completely ordinary. There would be no sudden slowing sensation, no dramatic shift in experience. It would simply continue falling, crossing the event horizon in what feels, to itself, like an unremarkable amount of time, even though outside observers would never see that crossing happen at all. This mismatch between what a falling observer experiences and what a distant observer sees is one of the strangest consequences of gravitational time dilation taken to its limit. Two perfectly valid points of view describe the same event in completely different ways, neither one wrong, simply describing time from two very different vantage points. Astronomers have gathered strong evidence for black holes through their gravitational effects on nearby stars and gas, through the shadow-like image captured of a black hole at the heart of a nearby galaxy, and through ripples in space-time detected from black holes merging together, ripples that themselves carry subtle signatures shaped by relativistic timing. These merging events, detected using incredibly sensitive instruments built to sense space-time stretching by a fraction smaller than the width of an atom, rely entirely on relativity's predictions to be understood at all. Without accounting for how gravity bends both space and time, these signals would remain meaningless static rather than meaningful astronomical messages. Even short of an actual black hole, extremely dense stars called neutron stars produce measurable gravitational time dilation, confirmed through careful timing of pulsing signals they emit as they spin. These pulses arrive at Earth with tiny, predictable timing shifts that match general relativity's equations closely, offering yet another confirmation from an entirely different corner of the sky. There is something almost humbling about contemplating a black hole's edge, a place where our familiar sense of time stretches nearly to its breaking point, where falling forever and freezing in place can somehow both be true, depending only on where you happen to be standing when you watch it happen. Part 9. Two Twins and the Trip Through Space. Let us return gently to the twin paradox and imagine it fully, since it offers such a clear way to picture time dilation acting over an entire human lifetime rather than over billionths of a second. Picture two twins, both born on the same day, sharing an identical childhood, growing up side by side on Earth. One twin stays home, living an ordinary life, aging 1 year for every year that passes. The other twin boards a spacecraft capable of reaching speeds close to the speed of light and sets out toward a distant star, planning to turn around partway through the journey and return home once the voyage is complete. From the perspective of the twin who stayed behind, the traveling twin's clock, and indeed the traveling twin's entire body, ages more slowly throughout the journey because of how quickly the spacecraft moves. Years pass on Earth, while aboard the ship, a comparatively smaller stretch of time passes for the twin making the journey. When the traveling twin finally returns, they step off the spacecraft younger than their twin who remained on Earth, sometimes by a difference of years, depending on how close to the speed of light the ship managed to travel and how long the round trip lasted from the perspective of the twin left behind. This might sound like a paradox, since motion is normally something we describe as relative, and it might seem, at first glance, that each twin could equally claim the other one was the one truly moving. But the situation is not perfectly symmetrical, and that asymmetry is exactly what resolves the paradox and gives us a clear answer. The traveling twin must accelerate, decelerate, and turn around at some point during the journey, while the twin who stayed on Earth remains in one steady, unaccelerated state the entire time. This difference breaks the symmetry between them, and careful calculation confirms that it is indeed the traveling twin who ends up younger upon return. While no human has yet travelled anywhere near close enough to the speed of light for this effect to become dramatic, astronauts aboard spacecraft orbiting Earth do experience an extremely tiny version of it. Astronauts who have spent long periods aboard orbiting stations return having aged a small fraction of a second less than those who stayed on the ground. It is a strange thing to consider that the very same laws confirmed by muons and aeroplane clocks and orbiting satellites would, given a fast enough spacecraft, allow a person to return from a journey younger than the sibling who waited patiently for them, both having lived every single moment fully and normally from their own point of view. Two lives, equally real, equally lived, and yet unfolding at different paces, simply because of the paths each one took through space. Time is not cheating either twin. It is simply honouring the different journeys each one made through the same shared universe. Part 10. Every now is someone's own now. We have travelled a long way tonight, from tiny particles falling through the sky, to clocks flown around the Earth, to satellites overhead, to the crushing gravity near a black hole, to two twins living different amounts of a shared lifetime. What ties all of these stories together is one simple, strange truth about the universe. There is no single, universal now, shared identically by everyone, everywhere. What counts as happening at the same moment depends on how you are moving and where you are standing in a gravitational field. Two careful, honest observers can disagree about whether two events happened at the same time, and both can be correct. This means the present moment you are experiencing right now, listening to my voice, is not quite the same present moment being experienced by someone moving quickly through space, or by someone standing near a massive star, or by an astronaut aboard a spacecraft far above the Earth's calm and familiar surface. None of this makes the universe feel unstable or unreliable to me. Quite the opposite. It suggests a deep, careful consistency, a universe that plays fair according to knowable rules, even when those rules ask us to give up comforting assumptions we once held about time flowing the same way for everyone, everywhere, always. Einstein did not stumble upon this idea by accident. He followed a single strange, well-confirmed fact that light always travels at the same speed, no matter how you move, and let it lead him wherever the logic demanded, even when that logic dismantled centuries of assumptions about how time itself must behave. What began as a patent clerk's careful thought experiment became one of the most thoroughly tested ideas in all of science, confirmed by falling particles, flown clocks, orbiting satellites, and merging black holes far across the universe. Few ideas in human history have been checked so many times, in so many different ways, and held up so consistently. Perhaps what I love most about this subject is how it reframes something we usually take entirely for granted. Time, the thing we spend our whole lives racing against, worrying about, wishing we had more of, turns out to be flexible, personal, shaped by motion and gravity rather than fixed and identical for every living thing. Your now belongs to you. It is shaped by exactly where you are, exactly how you are moving, part of a vast, quiet pattern stretching across the whole universe, connecting muons in the upper atmosphere to satellites overhead, to black holes light years away, all following the very same gentle, careful rules of relativity. As you drift off tonight, you might picture your own clock, ticking quietly at its own particular pace, part of an enormous cosmic fabric that stretches and bends around every planet, every star, every falling particle. You are not separate from that fabric. You are woven into it, resting inside it right now. And on that note, we come to the end of tonight's journey through time dilation and the relativity of now. We began with a simple, patient question about the speed of light, and found ourselves led all the way to falling particles, flown clocks, orbiting satellites, and the crushing gravity surrounding distant black holes. What strikes me most, lying here thinking it over, is how gently the universe reveals its strangest truths. Nothing about time bending was ever forced upon us through drama or spectacle. It emerged from careful measurement, patient reasoning, and a willingness to trust the evidence, even when it defied every comfortable assumption. There is something soothing in realizing that even something as fundamental as time is not rigid, not harsh, not indifferent to circumstance. It bends gently according to knowable rules, the same way a river bends around a stone without losing its overall direction, still carrying everything forward patiently toward wherever it is going. I think often about how small our daily worries become when placed beside ideas this vast. The stress of tomorrow's schedule, the small frustrations of today, They still matter, of course, but they exist inside a universe so much larger and stranger than the narrow slice we usually notice, one governed by wonders far beyond our little worries. Tonight's story was about a quiet kind of relief, the reassurance that comes from realizing our small, personal now is part of something enormous, patient, and consistent, something that has been unfolding steadily for billions of years before we arrived. When I imagine muons raining down invisibly above us, or clocks quietly drifting apart aboard airplanes circling the globe, I do not feel small in a diminishing way. I feel gently placed, held within a much larger pattern, one that keeps behaving the same reliable way, whether or not anyone happens to be watching it closely tonight. Thank you so much for spending this time with me here at the Nocturnal Astronomer. I hope tonight's journey through time dilation offered you a little of the calm it offers me, a reminder that even the strangest truths about the universe can feel, in the end, remarkably peaceful and reassuring. Until next time, let the vastness of the cosmos carry your worries gently away, one slow, patient, ordinary moment at a time.